Before we yeah, sorry, lost my train of thought. Before we get into the actual math of electrostatics, I want to motivate why we care about this stuff, right? So, in physics, yeah, in physics, all right, in physics we have four core subject areas that physics undergrads and physics grad students tend to. Ooh, thank you, Bach, for the follow. Oh, subscribe. Thanks. So yeah, there are four main subject areas in physics that physics undergrads and grad students do pretty much over and over again at different increasing levels of difficulty. So the first one you tend to learn um, is classical mechanics. So this is your very basic. We want to know how things move and why things move. So that's where you learn about force F equals ma, kinematics, that kind of stuff. Um, you have thermo slash statistical mechanics. Um, Generally speaking, um, thermodynamics and statistical mechanics is the study of how large systems of particles behave. Um, so temperature isn't the property of an individual particle. Um, there doesn't make sense to talk about the temperature of a single atom. Um, Temperature only means something when you're talking about the average energy that a system of particles have. But uh, yeah. Also, personal anecdote: fucking hate thermo and statmech. That is my least favorite of the four. Um, and yes, I realize the irony of the fact that my research involves a lot of statmech. But I do not do theory, so I don't have to worry about it. Um, Next is arguably one of the more famous ones, quantum. Uh, this is how the study of how small particles behave. Um, these classical and quantum tend to be um, and antitheses of each other. Because as you get smaller and smaller, objects do not behave the way we expect them to at the size scale that we're used to. And then finally, what we're going to be talking about today is electricity and magnetism, which is the study of how charged objects interact and the consequences thereof. So basically, electricity and magnetism. Um, so relativity is. So I'm going off of. These are what we consider in physics the core subject areas that every physics major has to learn. If you study something like astrophysics or cosmology, then you'll take a GR elective, and you do cover a little bit of special relativity in physics 3 slash a little bit in electro E&M, actually. Towards the end of this journey, I will touch on some special relativity. Um, but relativity isn't typically considered a quote unquote core subject in physics, if that makes sense. Um, so, yeah. So, charge is a fundamental property of certain objects, right? It's sort of like you have an object and they interact a special kind of way that we've observed. Um, and what we've noticed is that, all right, objects with this property that we call charge behave in general kind of like this. Oh, there we go. If I have two objects with the same type of charge, both positive charges, they will want to repel each other. Same thing if I have two negative charges. Um, and on the other hand, if I have two objects that have opposite charge, what we've observed is that they want to attract towards each other. And so a good example of this is actually a Van de Graaff generator. So if you don't know, a Van de Graaff generator is this machine right here. It runs a rubber belt across a metal brush, essentially, and that friction rubs excess electrons from the rubber belt onto the metal brush, which is connected to this sphere. So the charges, you'll have an accumulation of charge on the surface of this sphere. And what you'll see in this video um, is that the strands of string or hair that get charged from this Van de Graaff generator, because all of the electrons on the Van de Graaff generator move to the hair strands, all the hair strands become negatively charged. And because they all have the same type of charge, they want to repel each other, which is why they all fray out and separate. Same thing happens to human hair. Um, so yeah, that's so charge is the fundamental quantity that we care about when we talk about electrostatics. Um, so we are going to start with electrostatics. I just clicked on you. There we go. All right. Oh, thank you, Tyler, for the. Yeah. What's up, Oreo? Hmm. I need to make a question redeem, or like a raise hand redeem. Now I'll work on that. But yeah, what's your question? Oh, thank you for the 3 stream streak, Tyler. I'm Look, I'm getting used to this, okay? Monkeys saying monkeys jumping on a typewriter, right? True, there is highlight message. You mean like monkeys typing on a typewriter will eventually write Shakespeare? Yeah. Um so yeah. Electrostatics is where we're gonna start with our study of E&M. So electrostatics, as the name suggests, is the study of stationary charges. Because if you have moving charges, that gets complicated. That gets dealt with later. So the simplest, um, um, that more has to do with, I guess, probability. Um, Yeah, I mean, I guess it's a hyperbole. At least that's how I've always interpreted it. Um, because the odds of any string of a set number of letters forming a word is, I mean, I don't. That's uh, a statistics question, and that's more Mylan's area. But yeah. So yeah. So the easiest thing to start with is non-moving charges. And so how do we quantify? So as we've kind of indicated above, like charges repel and opposite charges will attract. So how do we describe this sort of behavior quantitatively? And so the answer to that is Coulomb's law. Coulomb's law states that the force between two charged particles is equal to q1 q2 over 4 pi epsilon naught r squared. R hat. Oh. Good job on the first, Comey. So yeah, where q1 and q2 are the charges of the two objects respectively. Um, epsilon naught. Yeah, technically Bach was first, but he didn't redeem it, so yeah. So epsilon naught is a constant that we call um the permittivity of free space. Um which basically describes how easy it is for uh basically describes how easy it is for electric fields to propagate in vacuum in free space. I'm not going to worry about the specific value of it right now, just because you can look that up. So yeah, the other thing to notice again, as we've discussed previously, force is a vector, which means it has a direction as well as a magnitude. And so what this tells us is that um, the direction of the um, the direction the force acts in is going to be directly in the direction of the separation between the two charged particles, right? So I guess I should probably actually let me rewrite this because this isn't quite accurate. This should be something along the lines of I don't like writing cursive R's, where this is equal to r minus r prime. So if r represents the position of charge particle 1 and r prime represents the position of charge particle 2, then the Coulomb force is going to point in the direction of the separation vector between them. And it's also proportional to the distance between them, squared. Ooh, Laplace's equation comes later, but don't worry, I'm really excited to get into Laplace's equation, uh, because not I mean A PDEs, but also B, uh, there's a specific method of solving PDEs that I want to talk about that Z has not done yet, as far as I know. Um, so I am looking forward to Laplace's equation, but that comes later. So yeah, so the next thing, so an important property of this Coulomb force is that it obeys the law of superposition. And what that means is, so yeah, there's all right. Let me finish this first. So law of superposition tells us that if I have a come on, there we go. If I have a bunch of charged particles, Q1, Q2, Q3, and I want to know how all three of these act on some test particle capital Q, then the total force on Q is just equal to the sum of the force from charged particle 1 plus the force from charged particle 2 plus the force from charged particle 3. That is the law of superposition. So yeah, uh guy, there separation of variables is the method that you tend to learn first, but there's also arguably a more powerful and generalized method. Um that's called the method of Green's functions. Yes, Oreo, that is precisely it. So the law of superposition is just addition, um, but it's an important property in physics because it preserves. It means that this behavior is linear. Um, but yeah, so to answer your question about what kind of physicist I am, so I'm currently a grad student and I specialize in um, experimental optics and material physics. So I study properties of materials by looking at how they interact with light, specifically laser light. Um, so yeah, which is also why I'm wanting to do this sort of thing on electricity and magnetism, because that is also a big part of what I do for research. So yeah, if I have, so yeah, let's expand this force, right? Um, if I were to actually write out all three of these forces using Coulomb's law, I would have 1 over 4 pi epsilon naught, since all those are constants, I can take them out, times the quantity Q1 over R1 squared. Remember, this is the separation vector between charged particle 1 and the test particle. So this would be R1. Uh, oops. I should write it out in vector form. R1 hat plus Q2. Oh, wait. Sorry, Q1 times the test charge. Q2 times the test charge. I'm skipping ahead. Plus Q times Q3 over R3 squared R3 hat. Um, and so, again, like I kind of just hinted at, you can also take the test charge, distribute it out of each of these forces. So I get Q over 4 pi epsilon naught times the quantity yeah, so that's kind of why I want to do this is I'm not I know physics is very math intensive. I'm not trying to get you guys necessarily to understand how to do all this math. What I want to do is get people to the point that if they see this, they see all this terminology, they see all these symbols, they can at least say, oh, this means that you care about this kind of behavior. If I give you a divergence, that tells you that I'm looking at whether or not something contains a source or a sink in terms of vector fields, that kind of thing. All right. So with this out of the way, um, I can group. What I can do now is group pretty much everything that isn't the test charge into its own quantity. And I'm going to call this quantity Q times E, where E um, is what I'm going to call the net electric field. So in this case, net meaning total. So yeah, this E is then equal to 1 over 4 pi epsilon naught times the sum. So again, remember this big sigma just means sum over the index I from 1 to n of qi ri squared ri vector. So yeah, this is how you calculate the electric field um, generated by an arbitrary sum of point charges, right? So this electric field is a vector field that is created by these source charges, little q. Um, and this tells us that the Coulomb force um, is proportional to the total electric field that the test charge capital Q experiences or feels from the rest of these particles. Um, so it's sort of it might be a bit hard to kind of visualize what this electric field actually is, because like most things in electricity and magnetism, it's not hard to visualize because this is some invisible vector field that charged particles experience. But you can kind of think of it, and you can kind of think of most force-like vector fields, as sort of like you know those like tile puzzles in Pokemon where you had like you stepped on it and it would move you here, 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 that kind of stuff. This is a similar principle, right? If I have a net electric field at this point that points this way, and this has charge total capital Q, then the force exerted on this charged particle is also going to go in the same direction, because like here, the force is proportional to the electric field, and since Q is a scalar, that means the direction is going to stay the same as the electric field. So this is how you would find the total electric field for P field of n point charges. But not there are very few things in this universe that are infinitesimally small that we can consider them point-like, right? Everything or most things that we see in everyday life have some sort of size to them. They have some sort of volume. Um, I'd put an asterisk on that guy. There is actually an experiment that gives evidence to the fact that the potentials, the electromagnetic potentials, are real. Because you get effects directly generated by them. But that's a quantum thing, and I'm not going to get into that today. If you want to look it up, it's called the Arnav-Bohm effect. Maybe I'll get into it later, because I also want to do quantum at some point. But yeah. So how do we find the electric field of generated by things that have a finite volume to them, that have a finite size to them? So what we do is we go back to our calculus. So if I were to break up any object into infinitely small pieces, then they would behave almost like point charges. So what that means is I can say the differential change, the infinitesimally small change in the electric field, is equal to the differential change in the charge of the object over 4 pi epsilon naught separation vector, separation vector. And so if we were to integrate both sides, the integral of 1 dE just gives us the electric field equal to 1 over 4 pi epsilon naught integral over your charge distribution of 4 pi epsilon naught r squared r hat. So, as it is, this integral is very hard to do because the way that the vector, this separation vector depends on the charge distribution is very hard to express numerically or analytically. So the 4 pi, so constants in physics are sort of tied to our definition of the units, right? So this epsilon naught has units of Newton Newton meter squared per Coulomb squared. Um, so the 4 pi is sort of an artifact of how we define our system of units. And it also, actually, yeah, it also comes up due to geometric considerations. Actually, so the 4 pi comes from the fact that the electric field is a inverse square field. Inverse square fields, meaning fields that decay as 1 over r squared, are very special in physics, and they have what we call spherical symmetry. And so you'll see later that this spherical symmetry gives rise to this 4 pi. In physics, pi is whatever you need it to be. You could consider it 1 if you really wanted to. Constants give you units, or at least, okay, my personal philosophy, I don't care so much about the constants, right? Since they don't change, they're not necessarily tied to behavior of a system, because the actual value of a constant will change depending on your system of units that you're working in. What I care far more about is how your variables change with respect to each other. I want to know if I change the distance or the charge of an object, how that affects the electric field and subsequently the electric force experienced by a test charge. So yeah, so this integral is hard to do as is, but to make it easier, we can talk about how to actually describe charge densities. So I can define 3 quantities: the line charge density, the surface charge density, and the volume density, or the volumetric charge density. And so these are defined sort of, as the name implies, as dq, dl, dq, dA, and actually I should do this to say defined. dq, dv. So dl, dA, and dv are all spatial quantities, right? Which means they are directly related to my separation vector, which will make this integral a lot easier to do. So that means if I have a line of charge, right? Like a wire, for instance, is a line of charge, or a straight wire at least. The electric field of a line charge, if I substitute these definitions in, is then equal to E equals 1 over 4 pi epsilon naught integral of the line charge density as a function of r prime. R prime being, by convention, the position of the source charge. Um, we use R without the prime to denote the test charge position by convention. Um, Separation vector dl prime over r squared. Where this L prime is the infinitesimal line element. If you remember back to last week's lecture, dl prime denotes the path integral element. So you're integrating along whatever path the line charge takes. For surface charge, it'll look similar. E will equal, again, 1 over 4 pi epsilon naught integral of sigma r prime r squared r hat dA prime. And finally, the volume charge density will, as some of you or all of you probably predicted, will be a volume integral, not over sigma. Volume integral of rho r prime dV prime. So these are, generally speaking, the equations to find the electric field directly of any continuous charge density of varying symmetries. If your charge distribution has line symmetry, then you use the top one. If it has a surface-like symmetry, use the second one, and so on. Any questions so far? All right. So let's do an example with this. So let's say that, nope. It's sort of a generalization, right? So as I said earlier, there are very few things in the universe that are actually point charges. Um, so you can think of any continuous charge distribution, right? Like if I had a blob of charge, um, and it has some volume distribution, you can kind of think of it as just an infinite sum of tiny infinitesimal point-like charges. So it's sort of kind of like how we did last week with the vector calculus, taking the simple algebraic form and turning it into the more powerful and more general calculus form. So this is more general than this. This only applies to point charges. Does that answer your question? All right, in the meantime, I'm going to set up this example. All right. I don't want it to have that shadow. What if I just... There we go. Okay. So, let's call this axis X and this axis Z. Yes, guy. Yes. Sorry. I maybe should have written that out explicitly. Um, but yes. The dimension of each of these uh infinitesimals, differential elements, tells you how many integrals you do. So again, so this is kind of just shorthand for a surface integral. A mathematician will get mad at me. So technically, um, what these should look like, this should be a double integral, and this should be a triple integral over the volume element. Yes. But yeah, because you can tell how many integrals you do from the dimension of the infinitesimal, most physicists just kind of keep it to one integral and just generalize. Um, yeah. We do a lot of shorthand that mathematicians do not like. Like treating derivatives as fractions. Technically, they're not fractions, but they behave like fractions enough, so we treat them like fractions. So charges are made up of many. Yes, yes, that's basically what this is saying. So an integral is saying you add up a bunch of things that are infinitely small. So it becomes what we call an infinite sum, and so it will turn into this integral. Whenever you think of integral, just think adding up. Just as when you think of derivative, just think rate of change. So yeah, so let's assume that we have a line of charge along the x-axis. We have a line of charge of length. Yes, Comey, yes. Um, yeah, so let's say we have a line of charge that goes from negative L to L. So it has length 2L. And we want to know what the electric field is at some point on the z-axis called point P. So, first, let's figure out how we define our source vectors and our observer vectors. Yes, to take incrementally small steps. Um, you can kind of think of it like frame rates, right? So a movie kind of looks continuous, right? You can see continuous motion. Most like high quality films are very smooth and flowy, um, but ultimately they're still made up of millions upon millions of pictures, basically, that you flip through to get the illusion of smooth motion. Um, that's sort of like how calculus takes algebra and kind of smooths it out. So yeah. So since our observer is along the z-axis, I can say that r hat or r vector is simply z z hat. Just as our line charge is along the x-axis, our source point will be x hat. And our infinitesimal line element, since the path is just a straight line along the x-axis, is just going to equal dx prime. So yeah. So that tells us that our separation vector is r minus r prime. I can write that out better. Is going to equal z hat minus x hat. Again, using vector subtraction. Um, so this separation vector actually looks like an arrow going from the x-axis to point P. So this is technically r hat, or script r hat. Okay, so next we need to know what the magnitude of this separation vector is. Um, so again, what we learned during our first lesson, we can use Pythagorean theorem to say that this is just equal to x squared plus c squared. And that finally tells us that our unit vector, which if you'll recall, is just the vector over its magnitude, so it has unit magnitude, um, is just equal to z hat minus x hat over the square root of x squared plus z squared. So that's what we need to get started with finding our electric field. So since this is a line charge, we will use the line charge formula. So E equals 1 over 4 pi epsilon naught integral of lambda r prime r hat over r squared d l prime. Wait, what's that? What's the no for? Oh. So yeah. So let's assume that it carries a uniform line charge, lambda. So uniform line charge just means as you go across the line, it's constant. So let's start filling in what we defined above. So since lambda is a constant, I can take it out of the integral. Mm. All right. So this is going to be z hat minus x hat over uh, the magnitude squared. But remember, the unit vector also has a magnitude, so this is the magnitude cubed, basically. So z squared plus x squared to the 3/2 dx. Oh, and our limits of integration are along the line of charge, so negative L to L. Okay, so let's split this integral up into the vector components. So this is going to equal lambda 4 pi epsilon naught quantity. Again, since we're only integrating along x, z is treated as a constant, so it can be taken out of the integral of dx over x squared plus z squared to the 3/2 minus x hat. The x cannot be taken out of the integral. I mean, she is a photon, and photons do travel at constant speed, so I mean, kinda, she's a constant. X dx x squared plus z squared to the 3/2. Okay. Um, yeah. So this first integral. Um, hmm. How many magnitudes of order? Um, so yeah, okay. So yes, this is a good place to kind of stop for a bit and make sure we're on the right track. So as Oreo pointed out, we want a way as we're doing these problems to make sure we still have the right kind of units to make sure we didn't mess up any math, right? So um, this is position to the one. Um, dx because you integrate over dx also counts as a unit. So this is going to be position squared over position cubed because you have position squared square rooted. So total, this becomes position squared over position cubed. So 1 over position. What we want is 1 over position squared, but remember lambda is charge over position. So yeah. I'm not going to bore you with the actual evaluation of the integrals. Um, what ends up happening is that this integral is 0. And you can kind of already look at it from symmetry, right? If you have the same charge on the right side as the left side, then the uh, then the electric field along the x-axis, because remember on the left side this will be your separation vector, the x components cancel out. Um, so the only non-zero component of the electric field that point P will experience is along the z-axis. And so this ends up equaling 2 lambda L times 4 pi epsilon naught z times square root z squared plus x squared. No, sorry, not x squared. L squared. Z hat. And so what this tells us is that, again, we have position squared square rooted, so that's position to the 1, and then multiplied by position, so that's still our 1 over r squared. But we have a length up here, so what does that tell us? Well, if you remember, oops, we defined our line charge density. Sort of, yeah. Um, so our line charge density is d q d l, but since it was constant, that also tells us that it's equal to the total charge over the total length. Um, so this part right here is just the total charge on the line. So yeah, and um, and uh, sometimes we also want to know what happens to the behavior of this field at extremes. So 2 lambda L over not z square root z squared plus L squared z hat. So what happens? Yeah, the x components, right? So if we go up to the diagram, right, this line of charge goes from negative L to L. The electric field on the left side of the rod is going to be pointing this way. And then the electric field on the right side of the rod is going to be pointing this way. So as you can see, the x components are opposing. They go in opposite directions. So they end up canceling out. And so the only thing you're left with is the z components, which both point upwards. So what happens as we move really far away from the rod? So really far away from the rod, we can say that z becomes much, much greater than L. And so what happens when z becomes much, much greater than L, um, we can treat L as approximately 0. Just because, yes, Oreo, exactly. They cancel each other out. The x components. Um, so yeah. So because z becomes so much larger than L, any contribution from L becomes so insignificant, we can treat it as 0. So what this means is the electric field approximately becomes equal to uh, 2 lambda L um, over 4 pi epsilon naught. Again, so, okay, I'm not getting rid of the L in the numerator because it's not, there's no operation tying it to z. But in the numerator, this z squared plus L squared, because z is much, much larger than L, this effectively just becomes z squared, square root. Um, so this becomes z squared. And as I said above, the numerator is just the total charge. So this kind of just looks like the equation for a point charge. And this is a very important fact. As you move infinitely far away from any charge distribution, every charge distribution will look point-like at some distance. I mean, despite the fact, Oreo, you're still following along very well. Um, that's also part of why I didn't want to go over actually calculating these integrals. Um, Again, I'm a physicist. I'll leave those kinds of details to a mathematician. If you really want to do it, you can throw it into like a programming language like Mathematica. All right. Yeah. And that ends our section on Coulomb's law and electric fields. So basically, what we've done to kind of summarize, we have introduced how charged particles interact with each other through Coulomb's law, Coulomb's force law, right? So the force between two charged particles behaves as 1 over r squared. Because of the way that this is formulated, we can also define the force, the electrostatic force, as your test charge times the total electric field generated by your charge distribution. And then finally, we looked at how to calculate the electric field of a charge distribution using what you'll see later is the brute force method. This is a very brute force method because it involves solving very tricky integrals. Um, there is a shortcut that exploits the symmetry of problems. And that method is called Gauss's law, which we will cover next week. And the important trick of Gauss's law is using a suitable Gaussian surface. So yeah, next week. Hey Eggy, how are you? Um, yeah. So next week, I will teach you how to avoid these integrals. Yeah. Um, so yeah, any questions on what we've covered so far? I know I keep teasing it. Next week is gonna be super, super big. Oh, tired. Have you had your interview yet? How to calculus. No, no, no. All right. This is what I like telling undergrads. Um, the entire point of a physics degree is learning how to avoid calculus and how to not do it. Um, because doing math is for nerds and mathematicians, and we don't like doing that. Yes, how to addition, or how to tell a computer to do addition for us. So yeah, just as universe the universe tends to be lazy and take the path of least resistance, so too do physicists. So yeah, Pep. All right, before I wrap up, I did promise you frogs. So I did mention earlier in my Discord in my villa that there are optical devices that has specifically been acronymed the frog and grenouille, which is French for frog. So I'm going to tell you about them. So let me go back to my window source. Boom. Um, oh, the lambda bit? Sure. Uh, you mean like the problem we just did? What about it?